So, chemical bonds. This is methanol. This is not the alcohol you want to drink. Ethanol is the alcohol you want to drink. All right? Methanol is the alcohol that moonshiners sometimes accidentally make. It's called wood alcohol. It destroys your optic nerve and you go blind. All right, let's have a save. Okay, no, I'm going to fill up my shot glass here. All right, and I'm going to set this on fire. The nice thing about methanol is that it's extremely clean burning. It takes the methanol molecule, which I'll give you a lot more detail about Friday, and it turns it into carbon dioxide and water vapor. That is actually on fire, even though you can't see it. And did we bring miscellaneous paper to burn? Yeah, well, this work. All right. And you can tell it's on fire because if I put something over it, it catches on fire. All right? There we go. That's why they give me a sink. All right. So this is a chemical reaction. Energy results because I'm taking that alcohol molecule and then breaking it into more stable molecules, carbon dioxide, water vapor. Friday we'll put numbers behind it. The key thing here is to think in terms of rearranging chemical bonds. The reason it's hot, and believe me, if I put my hand up here, I can stand it. Here, here, more pain, more pain. That's not pain. And it's because the molecules that, the more stable ones, the things we turned it into, are moving very quickly. When they're moving very quickly, faster than the molecules in my hand, and they hit the ones in my hand, they start, quote, warming up my hand, which means the molecules in my hand are moving faster. If the molecules in my hand are moving faster, at some point my nerves say, hey, you're getting burned, idiot, move your hand. All right? Usually my wife here, who came first day of class in Maryland, is the one that has to tell me to move my hand. All right, but yes, I've got a flame going on. I also want to point out something that will be a recurring theme through all of this energy discussion. That's a fossil fuel. You could have made it and distilled it from oil. It's a liquid fuel. And liquid fuels are so incredibly easy. You realize you could power your automobile, this multi-ton large piece of steel, and maybe on 1 ounce it only goes, I don't know, a mile. That's pretty impressive, that you can take a couple ton piece of steel and move it a mile with an ounce of liquid fuel. Incredible energy density packed into there. Easy to transport, right? Right? Put it in bottles, put it in pipelines, have it in every pump someplace. Pretty stable. I mean, we'll bring in some nitroglycerin, that's not stable, but something like alcohol, pretty darn stable. You can pump it around, you can have it in buckets. This is our primary energy source for the world. Liquid fossil fuels, because they are so easy. There's an hope, of course, that you'll go to more renewables, nuclear, other possibilities, and to wean the world off of this, which is a potentially limited supply, but it's easy. And just think back to the fact that this little ounce is going to stay here and burn for some time. So rearranging chemical bonds. We're going to get a bit more complete combustion out of this. What I want to show to illustrate is they all come back to this. So let's take another form of energy here, electricity. Again, we'll have a whole topic on electricity. And right now I'm illustrating it because I have electrons. That's what electricity is, moving electrons. And those electrons are moving back and forth. This transformer doubles the frequency from the wall, so it's 120 times a second. And you can actually see electricity. Those electrodes are at 10,000 volts, not something I want to touch. All right? But I do want to show you that it's actually going back and forth. All right? That's kind of small. All right. Right, so if I take this piece of paper and put it between here, and don't let it catch on fire, aha! Tell me what you see if you hold that up to the light. You can take it. Hold it up to the light. That's holes! They're holes. Here, we'll make a bunch of them. Guys, help pass these up. All right. All right. There's holes because this is actually a lightning bolt going this way, and this way, and this way, and this way, 120 times a second. So we have 10,000 volts. All right. Go. That goes around. We have electricity. So how in the world is this rearrangement of chemical and nuclear? Well, remember, contrary to popular belief, electricity is not magically made by this little plug. All right? There's wires on the other side of that plug, and those wires will wind their way back to an electric power plant. These particular wires, and this is an older part of campus, winds its way back to the Abbott power plant, which you will have a tour of. And the Abbott power plant is fueled primarily by coal. They're going to phase out the coal, but right now, if you see smoke coming out of the really big smokestack, they're burning coal. And how do they burn the coal? Well, the coal is burned with the air, oxygen, and you are rearranging the chemical bonds, coal is mostly carbon, into carbon dioxide. It's a more stable state, and that's where you got the energy. Now the process of taking the heat energy, remember, we've got a burning fossil fuel here, right? We have heat energy. Taking that and turning it into electricity takes a few more steps. You have a turbine and a generator, and on whatever day it says electricity, you're going to learn everything about that. But the source of that power, if I trace it back, is rearranging the chemical or nuclear bonds. Electricity. All right, what do we got left? Not too much time. Let's move on. Okay, we want to stop that one. Let's move on to nuclear things. We got our fossil fuel burning. We got electricity going here, right? And we need to also have nuclear. So as an illustration, I have brought in a small nuclear device. And you have to be always a little careful with these. You have to always make sure not to, how do we get this here? Not to get the, oops, wrong button. What? If I let go, does it reset? Oh, no. Well, don't worry. I'm sure we can turn this off here. Get some stuff out of the way. If that gets down to 10, make sure to give me a countdown, all right? All right. I think I can just turn some of these switches, right, to turn it off.
Great. Try cutting a wire.
Wire, okay. Wire. God, there's a lot of wires. Red? Which red wire?
Any.
3, 2,
God, I hope this is the right one.
Jesus.
Thank you very much.
Look at your hand.
I can't see anything. Am I still up here? All right. Good job. If that was actually a real nuclear device, of course, this building wouldn't be here. That was a nice chemical explosion. But if it were a nuclear device, it does the same thing. You rearrange bonds into a more stable state. In this case, and it's nice because we have a periodic table in the room, uranium is the heaviest. Uranium is the heaviest naturally occurring element. And instead of taking the chemical bonds, like uranium combined with something else, we're actually taking the nucleus of uranium itself. Nuclei are made up of protons and neutrons, right? And they are combined together. Different nuclei have different stability. The reason uranium makes atom bombs is it's not terribly stable. And I can break uranium up, the nucleus, up into things that are in here. It still has to add up to 92, so maybe I make 41 plus 51. And I break this uranium up into these, and those elements, niobium and
Antimony.
Thank you, have more stable nuclei. So I can rearrange the bonds within a nucleus to make more stable state as well. Fusion energy, energy source of the stars, right? The energy source of, you might say, the far future. An energy source I work on in my research. Fusion takes hydrogen and forms it into helium. It's still a more stable state. Helium is actually a very stable nucleus. All of these things called the noble gases are very stable devices. Very stable elements. Rearranging a nuclear bonds, not bombs, into a more stable state is another way to release energy. And once again, the energy manifests itself as the movement of the products, okay? As the movement of the nucleuses that result. If I split this uranium, the niobium and antimony are going to be moving really fast. Probably ionizing all the air, making a lot of heat, making a mushroom cloud, and there you have it, right? But it's still rearrangement of bonds. Tell me what he asked. And hydroelectric, that's an excellent one. All right, follow it. The only reason you have hydropower, water falling off of a dam, is because it rains. It has to rain up where the thing is, right? It rains because water evaporates from the earth, forms clouds. Why does the water evaporate from the earth? The sun. And the sun combines hydrogen into helium. Rearrangement of nuclear bonds in the sun. Little did you know, hydropower, solar, all that's really nuclear power, done remotely in the sun of nuclear fusion. Rearrangement of nuclear bonds in the sun gives us sunlight. So all the things, solar, right? Here I have a little solar radiometer. I could have a solar cell going. This, of course, isn't really the sun. This is electricity, but you know, not exactly a lot of sun outside right now to illustrate. I remember used to do this, and I put the thing up there in the windowsill, and nothing would work, right? Because there wasn't any sunlight. Because it's January in Illinois. But I'll turn this off because this is very annoying to look at. That's where we get for hydropower. You know those weather maps you see on TV, and they got a big H and a big L, and they're moving across the country for high and low pressure? Wind blows from high to low pressure, right? Try to blow out your mouth, keep your lips closed. Right, that's got high pressure inside, low outside, wind comes out. That's how wind blows, high to low pressure in the atmosphere. Why do you get those H's and L's? Uneven heating of the ground. Gulf of Mexico, really warm, high pressure zones come up. Arctic, really cold, low pressure zones, right, come down. Giant Arctic vortexes in Gulf Central Illinois, and we all freeze to death. All right, you got the part picture. So wind comes about because of solar energy, and solar comes about because of the sun, and the sun comes about because of nuclear fusion, rearranging hydrogen into helium in the nucleus.